Let us take a look at another set of challenging questions on colligative properties. This time, we want to focus on non-dissociating solutes, which is another way of saying covalent compounds. Let us begin with question number 1. A 1.06 molar solution of sucrose has a density of 1.14 gram per milliliter at 25 degrees Celsius. So we know the molarity and we know the density. This is the question. Predict the boiling point of this solution. The very first thing to note is that we always have an elevation in the boiling point of a solution relative to the pure solvent. And the equation for finding the elevation in the boiling point is change in the boiling point is equal to the boiling point elevation constant Kb multiplied by the molality of the solution. Now, let me say that again. Molality, not molarity. But we were provided the molarity. We need to know the molality. That is where the challenge in this question is located. Now, the very first thing we want to note here is that this value is going to be given to you, and it is usually given as 0.52 degrees Celsius per molal. So, how can we convert molarity and the density to the molality? The very first thing we want to write out here is that molarity is equal to the moles of your solute divided by 1 liter of solution. Moles per liter. In this question, we do not know anything about the volume of the solution. So, we're going to make an assumption for it. Let us assume that we have 1 liter of the solution. You only get to make this type of assumption if you need the volume and nothing about the volume was offered to you. Let us now continue. This means that 1.06 molar given to us is the same thing as 1.06 moles of the solute, which in this case is the sucrose, per liter of solution. And that means we now know the moles of sucrose. Since we are making an assumption of 1 liter of the solution. Why is it important that we know the moles of the solute? The reason is because molality, which is what we need to find the change in the boiling point, is equal to moles of the solute divided by kilogram of solvent. So one piece of the puzzle is solved. The next problem is, how do we find the kilogram of the solvent? And for that, we're going to take a look at the density. From the density, we should be able to find the mass of the solution, because we know that density is equal to mass divided by volume, which implies that density times volume is equal to mass. We know the density of this solution. The density is 1.14 gram per milliliter. And we already assumed 1 liter of the solution. And 1 liter is 1000 milliliter. If we multiply these two, milliliters will cancel out. That will give us the mass of the solution. And this would work out to 1140 grams of solution. Now, to find the mass of the solvent, we need to know the mass of the solute, because we know the moles of the solute. So if we have 1.06 mole of sucrose, from the periodic table, we know that 1 mole of sucrose would have a mass of 342.30 grams. If we cancel out moles of sucrose and we multiply 1.06 by 342.30, we should get 362.838 grams of sucrose. With that known, we can now find the mass of the solvent. The mass of the solvent, which in this case is water, will be equal to the mass of the solution, which we already calculated as 1140 grams. We will subtract the mass of the solute from that, and that will be 362.838 grams. And this should give us 777.162 grams of the solvent, which is water. And that is the same thing as 0.777162 kilogram of solvent. So we can now find the molality of the solution. The molality will be equal to the moles of the solute, which is 1.06 mole divided by the kilogram of the solvent, which is 0.777162 kilogram. And that works out to 1.363936 molal. Let us now find the boiling point elevation. So delta TB will be equal to 0.52 degrees Celsius per molal multiplied by the molality of the solution, which we calculated as 1.363936 molal. The molal will cancel out, and if you put this into the calculator, you should get approximately 0.71 degrees Celsius. Now, we want to find the boiling point of the solution. The normal boiling point of water is 100 degrees Celsius. So, if the boiling point is elevated by 0.71 degrees Celsius, then the boiling point of the solution will be equal to 100 degrees Celsius plus 0.71 degrees Celsius, which is equal to 100.71 degrees Celsius. Let us now focus on the B part of the question. Predict the vapor pressure of water over this solution at 25.0 degrees Celsius. The vapor pressure of pure water at 25 degrees Celsius is given as 23.76 torr. To find the vapor pressure of water over a solution, we will need to make use of the Raoult's law. And what does it say? The pressure above a solution will be equal to the pressure of the pure solvent, which in this case is given to us, multiplied by the mole fraction of the solvent. So to solve this problem, all we need to do is find the mole fraction of water in this solution. Remember that the mole fraction of the solvent will be equal to the moles of the solvent divided by the total mole of the solution. Do we know the moles of the solvent in this question? No, we do not, but we know the mass. And the solvent in this case is water. So let us find the moles of water. The moles of water will be equal to the mass of water, which we calculated as 777.162 grams, multiplied by 18.02 grams of water from the periodic table is equal to 1 mole of water. Grams will cancel out. And if you divide, you should get 43.1277 moles of water. We already know the moles of the solute, that is from the molarity given to us at the beginning. So the mole fraction of the solvent will be equal to 43.1277 divided by 43.1277 plus 1.06, which is the mole of the solute. And if you divide, you should get 0.97601. Let us now calculate the vapor pressure over this solution. The vapor pressure over the solution will be equal to the pressure of the pure solvent, which is 23.76 torr, as you can see here, multiplied by the mole fraction of the solvent, which is 0.97601. If you multiply, you should get 23.19 torr. Let us now take a look at question number 2. A solution containing 0.674 gram of one type of interferon. I know you are thinking, what are interferons? Interferons are naturally occurring proteins. They boost immunities against viral infections. Interferon has actually been tried on coronavirus. It was discovered that it leads to what is called cytokine storm, which is an overstimulation of the immune system, and that also is deadly, which is probably why we are not hearing a lot about interferons. Anyway, so we have 0.674 grams of interferon in 157 milliliter of our solution. And this solution has an osmotic pressure of 4.15 torr at 25 degrees Celsius. We are required to calculate the molar mass of this type of interferon. So our goal is to know the molar mass. Osmotic pressure is another colligative property, and the relationship between osmotic pressure and molarity is given as osmotic pressure equals to the molarity of a solution multiplied by the molar gas constant multiplied by the temperature in Kelvin. So the question is, how can we use this relationship to find the molar mass of interferon? Remember, interferon is a protein. You should expect a very big molar mass. So, how do we go about this? If we can find the molarity, we can use the molarity to find the mole, and we can then use the mole to find the molar mass. So let us find the molarity. Let us isolate the molarity from this expression. Molarity will be equal to the osmotic pressure divided by the molar gas constant and the temperature also in the denominator. Let us plug in the values. But before we do, let us be very careful with the units. Let us begin with the osmotic pressure. The osmotic pressure is given to us in torr. However, the molar gas constant R is given as 0.08206 liter atmosphere per Kelvin per mole, and this value is always provided, which means that in this molar gas constant, the unit of the pressure must be in atmosphere, And that means we need to convert the osmotic pressure also to atmosphere. So the osmotic pressure will be equal to 4.15 torr multiplied by 760 torr is equal to 1 atmosphere. And if you put this into your calculator, you should get 0.0054605 atmosphere. Also, the temperature is given to us as 25 degrees Celsius. Again, in the molar gas constant, the unit of temperature is in Kelvin. So, we will need to convert the temperature to Kelvin, which means 25 degrees Celsius plus 273.15. That works out to 298.15 Kelvin. Now we are ready to find the molarity. Let us plug in the numbers. Molarity will be equal to the osmotic pressure, which is 0.0054605 atmosphere, divided by the molar gas constant, 0.08206 liter atmosphere per Kelvin per mole, multiplied by the temperature, which is 298.15 Kelvin. Kelvin will cancel out, atmosphere will cancel out, which means we're going to end up with the unit of mole per liter. And my calculation gives me 2.231866 times 10 to negative 4 mole per liter. Remember that moles per liter is the same thing as molar. Now we know the molarity. Remember our plan, we want to use the molarity to find the moles. So let us find the moles out of the molarity. From the question, we were given the volume of the solution to be 157 milliliter. So the volume is known as 157 times 10 to negative 3 liters. 10 to negative 3 is the same thing as milli. And we know that molarity is equal to moles per liter of solution, which implies that mole will be equal to molarity multiplied by liter of solution. Let us plug the numbers in. The mole of this interferon will be equal to the molarity, which we just calculated as 2.231866 times 10 to negative 4 moles per liter, multiplied by the liter of the solution, which is 157 times 10 to negative 3 liters. The liters will cancel out, which gives us the unit of moles as we want. And if you put these numbers into your calculator, you should get 3.5043 times 10 to negative 5 mole. Now we know the mole. We can then use the mole to find the molar mass. Let us again go back to the question. In the question, we were given a mass of 0.674 grams. Let us now use the mole and the mass to find the molar mass. Remember that molar mass has a unit of gram per mole. So, to find the molar mass, we simply will divide the grams by the mole, which will be 0.674 grams as provided in the question, divided by 3.50403 times 10 to negative 5 mole, which we just calculated. And if you put all of these numbers into your calculator, you should get 19234.99 gram per mole, which if rounded to 3 significant figures would be 19200 gram per mole.